Now we want to talk about the chain rule. The chain rule is what allows us to take the derivative of functions that have been composed together. So by composition, we're talking about a function inside of a function. So when you take the derivative of a function inside of a function, this is what we mean by the chain rule. There are different ways of forming new functions out of old ones. We can add functions, subtract them, multiply them, divide them, as long as we don't divide by 0. But we can also compose them. By composition, that means you take one function and you substitute it inside of another function in place of the variable x. So you're substituting a function in place of the independent variable, usually x, but it could be t or something else. When we do that, though, we end up with a composition of functions. So this could be something like putting a polynomial under a square root. So you've got the polynomial, which is one function, substituted inside of another function, which is the square root. And the question is, how do we take the derivative of a function inside of another function? How do we take the derivative of a composed function? In order to do that, we need what's called the chain rule. The chain rule is used probably on at least 70 to 80% of the problems that you'll see in Cal 1, Cal 2, and Cal 3. It gets used all the time. It is rare to have a problem that doesn't involve the chain rule at least a little bit. So you should become at least 95% proficient at doing the chain rule. If you're not 95% proficient at doing the chain rule, you're probably not going to make it into Calculus 2. All right, it's just probably not going to happen. And so let's take a look at deriving the chain rule. And here's another example of a composed function where we have a function x squared plus 4 substituted inside of another function, which is x cubed. So you can think of these functions as f of x equal to x cubed and g of x equal to x squared plus 4. And what I have is f of g of x, or in high school, sometimes they call this fogging and goffing, right? With that circle notation that is an open circle, not a closed dot for multiplication, but an open circle indicating composition. So we took G and we put G inside of F in place of the variable X. So this is actual composition of two functions, all right? Now, in theory, I could multiply this out 3 times and get a polynomial, and then I wouldn't have to worry about the chain rule. But what if it were raised to a higher power like the 33rd power? There's no way that I could spend the time to multiply this out 33 times. And even if I had the time, the chances that I could do it correctly and not make a mistake are extremely slim, right? I mean, the chances are extremely high that I would make multiple mistakes and it would be wrong. So instead, we use what's called the chain rule to break apart the composition of two functions. So we're going to let f and g be our two functions, and h of x is going to be our composed function, f circle g of x, or f of g of x. The derivative is given by f prime with g of x plugged inside times g prime of x. And I'm going to write this a little bit larger the way I normally write it, with different sizes of parentheses. All right. Now, notice that the first set of parentheses here is larger than the inside. I'm taking the derivative of the f function and I'm substituting the g function in place of the variable. So take the derivative of the outside function, substitute the inside function in place of the variable x. Then this is a dot. This is a closed dot, which is not the same as the circle notation. This is a dot meaning multiplication. and I multiply it by the derivative of the inside function. So this dot is a multiplication dot, not an open circle. All right. So it's derivative of the outside, substitute the inside, times derivative of the inside function. All right. Derivative of the outside function, substitute the inside function, times derivative of the inside function. If we think of the outside function as a function of u, we can write this as dy du times du dx, where u is the inside function. All right. And notice that the du's would then cancel. All right. So there are two methods of doing this. I'll teach you both methods, but eventually you'll want to switch towards the second method, which is faster, but more of it takes place in your brain. All right. So there's less written down, but it is faster. Okay. We'll go through a brief version of the proof. This isn't the full proof because we're ignoring a couple of issues here, but we're going to do the basic proof. All right, so what is the derivative of the composition? Remember that we've defined h of x to be equal to f of g of x. And notice that the g of x is written smaller with smaller parentheses to show that it is inside the function f in place of the variable x. So I've substituted g in place of the variable x in the f function. What does that mean? Well, one of the definitions of the derivative that we covered was the x approaching a definition. The limit as x approaches a of f of g of x minus f of g of a over x minus a. So this is one of our definitions. In the denominator, what we do is we multiply by a form of 1. And keep in mind, it probably took somebody months to figure this out. I mean, literally months, sitting there day after day, pieces of paper going into the trash can because it wasn't working, right? Took them months to hit on the right way to do this. So you're seeing it now in 1 minute, but it took them months to figure this out. This is not easy. So they're multiplying by g of x minus g of a divided by itself. So this factor right here is equal to 1, as in the number 1, all right? But if we multiply it by 1, what we do is we slide the denominator underneath the first part of the fraction, and we pull the x minus a out. So looking over here, you can see the g of x minus g of a has gone underneath the original difference quotient, and we've pulled the x minus a out. We left the g of x minus g of a in the numerator. So now we have g of x minus g of a over x minus a over here being multiplied by the original. But they've got to be equivalent because remember in multiplication, order doesn't matter, right? 2 times 3 is 3 times 2. Things commute. So I can pull the order and change the order. It won't change the product value. Once I do that, then I've got the limit of a product and I can split it into the product of 2 limits. So I split the limit, one for the first and one for the second. Now the second one, this is just the x approaching a definition of the derivative of g. So this gives me g prime at a. So that part is the derivative. The first part is a little bit different. All right. Now, since g is differentiable at a, then it has to be continuous there. And that means by the definition of continuity, the limit of g of x has to equal g of a. So we have g prime of a. Right? Now, the next thing that we're going to do is we're going to make a short substitution. And we use the change of variables in the limit to get the following. So we let y be g of x. And we let b be g of a. all right, just to write it in a shorter method. So this means that I've got f of g of x becoming f of y, and g of x becoming y, g of a becoming b. So I've got g of a is b in the denominator. This gives me the definition then of y approaching b, which means that I've got the derivative of f at b, but b is g of a. So my final formula is f prime of g of a times g prime of a, which is the rule. Now there are two ways of doing it. In one, we make a substitution that the inside function is u, and we take a derivative of the outside function with respect to u, and then we take the derivative of the inside function u, and then we multiply them together. The fact that these two cancel, this is called an abuse of notation. Like we're beating the heck out of it. Okay, we're really not, but it is called an abuse of notation. Now, why is it an abuse of notation? This represents a derivative operation. This does not represent a fraction. Leibniz wrote it in fraction form, but it does not represent one thing divided by another thing. It represents the derivative of a thing with respect to that variable. So it's not a fraction at all, not at all. It's an operation called the derivative. But why did Leibniz write it that way? Because it works, all right? So you can abuse the notation and treat it like a fraction, and it works, all right? So I'll show you how this works out as we go through them, all right? So let's take a look now at example 1. In example 1, we're given that H is equal to the composition of F with G. So it's F composed with G, or F of G of X. Remember that F of G of X and G of F of X are rarely ever the same thing. Rarely. In fact, the only time they come out to be the same is when you have the identity function, right? That's the only time. Or something that is its own inverse, like the rational function 1 over x, all right? It is rare for them to be identical. This says if g of 2 is equal to -3, and g prime of 2 is equal to 4, and f prime of -3 is 7, find h prime of 2. Okay, so what are you supposed to do here? First thing we're going to do is we're going to write down the rule for h prime of x. H prime of x is going to be equal to f prime of g of x times, not dot, but not circle notation, but dot, sorry, dot for multiplication, times g prime of x. All right, so if I want to know what h prime of 2 is, then what I'm looking for is f prime of g of 2 times g prime of 2. Now, what is g of 2? This is g, not g prime. So g of 2 is -3. So this becomes f prime of -3 times. Now this part is g prime, so it's g prime of 2. And I'm looking, g prime of 2 is 4. So this is multiplied by 4. And then we want f prime of -3, which they gave us to be 7. So this turns out to be 7 times 4, which is 28, right? There are a couple of problems in the homework set like this, all right? There are a couple problems in the homework set like this, all right? Again, use the definition. H prime of x is equal to f prime of g of x, unchanged, the original g, times g prime of x. Then replace the x's with wherever you're trying to find the derivative, and then substitute each piece one step at a time. Now we're going to separate the composition so that we can find the layers that we have, because it's not common to just find one layer. Well, it is fairly common, but it's not uncommon to have multiple layers, to have a function within a function within a function. All right, so you could have the natural log of the square root of x squared plus 5. So you've got x squared plus 5 as one function, inside a square root as a second function, inside a natural log as the third function. So here are some things you want to look for when you're trying to figure out what the layers are. And when you're looking at these, you want to look for parentheses which show grouping, not multiplication. So if it's showing multiplication, it would be down on the multiplication level. But parentheses showing grouping, like x squared plus 5x plus 2 in parentheses, that shows grouping. If you have -2 in parentheses and then a 4 in parentheses, that's showing multiplication. So make sure you know the difference between the two. Parentheses showing grouping are a good way of finding where you have an inner function. Absolute values are another good way of finding inner functions. The argument to a natural log or to a trig function, that's another way to find inside functions. Things raised to constant powers, that's another way to find the inner function. And the things is usually parentheses, all right? So parentheses raised to constant powers, which gets back to parentheses showing grouping. When you have roots of some kind, when you have like a cube root or a square root or whatever is underneath it is the inside function, and the outside function is the root itself, right? Powers on Euler's number e. So if you have e to the 3x squared plus 2, then you've got 3x squared plus 2 inside e to the x, right? Fractions are another way to show composition, usually the denominator, but not always, sometimes the numerator. And then you can also think about the order of operations. Remember, the order of operations is parentheses, exponents and roots, multiplication and division left to right, addition and subtraction left to right. Okay, so really when we write PEMDAS, we really should write MDAS, all right? Because it's parentheses as a grouping symbol, which includes absolute values, exponents and roots, multiplication and division left to right, addition and subtraction left to right. Now, we never mess up the addition and subtraction, but you can mess up the multiplication and division if you don't do it left side to right side, all right? So when you ask yourself, what's the last thing I would do if I were plugging in a value for x, that last thing is usually the outside function. Okay, so what we want to do now is we want to identify some, and I'm going to give you a derivative that we have not had before. It actually isn't supposed to come until Friday in the schedule, but we need it before then to practice with it. So I'm going to give it to you early, and you will need this on your quiz as well. The derivative of e to the x is, it's our favorite, e to the x. You can see why it's our favorite, right? The derivative of e to the x is e to the x, right? There's nothing to do there. All right, so the derivative of e to the x is e to the x. So we want to practice pulling apart these composed functions. So when I look at 3x plus 7 raised to the 10th, I see two things. I see parentheses as a grouping symbol, grouping two terms, 3x and 7. And I see that group raised to a power. So the inside function is what's inside the parentheses. and this is going to be the 3x plus 7. And the outside function is x to the 10th. Or some people like to write it with a u. They might write u to the 10th, right? And then they would let u be the inside function, 3x plus 7. Okay? Let's take a look at the next one. We're looking at sine of x over 4. So when we look at sine of x over 4, again, we have parentheses around the argument. Sometimes I write them, sometimes I don't. I'm not as good at it as I should be. I should write them all the time, but I'm kind of lazy sometimes, lazy mathematician. But the parentheses around the argument indicate that this is inside of a sine. So the inside function is x over 4. And the outside can be written as sine of x or sine of u, whichever way you prefer to do it. And it depends on which method you use as well. All right. Let's look at the next one. The next one has secant of e to the x. We've got parentheses around the e to the x, which is the argument to the trig function secant. So e to the x becomes the inside function u. And the outside function is secant of x or secant of u. Is everybody seeing how I'm breaking these apart? Are there any questions? Not yet. Okay, let's take a look at the next one. You have e raised to a power. So again, if you were going to plug in a number for x, you like 2. First, you'd square it, then you multiply it by negative, then you take e and raise it to that power. So the last thing you did was e to that power. So the outside function is e to the x or e to the u, e to a power. And the inside function is that right there, right? So let's go ahead and write down the answers to the last 3. The answer to the next one is a little bit tricky, but if you again imagine, what would I do if I actually had a number like 1? I do 1 plus 2, which is 3, then raise that to the 5th. Then I do 1 cubed is 1 times 3 is 3, plus 3 times 1 is 3, so that'd give me a 6. And then I'd have 6 times that 3 to the 5th. And the last thing I would do is raise it to the 4th power, right? Last thing I do. Then that last thing you would do becomes the outside function. And the inside function is everything inside of it. All right, the last thing you do is the outside function. That makes the next one easier to do because the last thing I do would be to raise it to the 20th power. So x to the 20th or u to the 20th, whichever way you want to write it. And the inside function is 5x squared plus 11x. Similarly, on the last one, the last thing I do would be to raise the fraction to the 5th power. So x to the 5th or u to the 5th becomes my outside function, and the inside function becomes that fraction. Now, we have not done the derivative. All we've done is separate the composed function. The next thing we need to do is actually take the derivative using these pieces. We haven't done that yet.
So we need to talk about 2 methods to apply the chain rule. There are 2 basic ways to do it. One is using an actual substitution with u, and the other is to apply Leibniz's notation rule with dy dx being dy du times du dx. And of course, the other method, of course, is just to apply it directly, where you find the derivative of the outside function, substitute the inside function, and then multiply by the derivative of the inside function. When you apply the formula directly, most of the work takes place in your brain. and then it's written down directly. If you use the U substitution formula, then you write down most of the steps. So it takes a little bit longer. It's longer to do. And there's a little bit less guesswork. There's not really any guesswork in it, but there's less to do in the brain. Let's take a look at the U substitution and Leibniz's notation rule. This method basically takes two different parts of the equation, the outside function and the inside function, and pulls them apart. It rewrites the outside function in terms of U, and then it rewrites the inside function so that U is equal to the inside function. It takes the derivative of the outside function with respect to U, then takes the derivative of the inside function with respect to X, and then it multiplies the two together. Finally, the last step is to substitute back for U. So you're going to replace that inside function with U, take the derivative of the outside function then with respect to U, find the derivative of the inside function with respect to X, multiply the results, and then substitute the inside function back in for U. So let's take a look at one example of this using sine of X squared rather. When we're looking at sine of X squared, we have two functions. We have an outside function, which is sine, and an inside function, which is X squared. So when we're looking at this one right here, we can think of sine of U being the outside function. And we can think of X squared as the inside function. So then when we apply the steps to using Leibniz's notation, we take the derivative of the outside function, which is now written as sine of U, with respect to U. So the derivative of sine of U would, of course, be cosine of U. And then we take the derivative of the inside function, which is X squared, with respect to X, which would give us 2X. And that would give us this result down here. Then we multiply the two parts together, which gives us cosine of U times 2X, which you see down here. And then the last step is to back substitute for what U is. And then when you back substitute for U, you get that U is X squared. And so your final result is cosine of X squared times 2X. So you get 2X cosine of X squared. Right? And this is the final result. Now, of course, the 2X could be written at the back, but the danger in putting it at the back is that it might look like it's part of the argument to the cosine. So we would typically move it to the front because cosine has an argument and we don't want to mistake the factor for the argument of the cosine function. Now, when we apply the formula directly, the steps are pretty much the same, but they mostly take place inside your head. So what you do is you find the derivative of the outside function, which in this case was cosine. So you would just write cosine, but you don't write down the argument, all right? So when you're looking at the original, so the original, of course, was sine of X squared. You take the derivative of the outside function, which is sine, and that gives you cosine. And then once you have that, you substitute the inside function, which is X squared, back inside of this cosine function. And then you multiply by the derivative of the inside. So you go back to the original and you say, well, X squared was on the inside and the derivative of X squared is 2X. And so it all gets done more or less in one single step. And you can see that the second method is much shorter and there's less writing to do, but most of the work that's happening is taking place in your brain. So you're having to actually talk your way through it. You split it into the outside and inside. You take the derivative of the outside and write down that part. Then you substitute the inside function for the argument. And then you multiply that by the derivative of the inside function. And this is the second method of doing it. When I do it, I usually say derivative of the outside frees the inside times the derivative of the inside. And this is a good way to think about the chain rule. So it's the derivative of the outside function frees the inside function times the derivative of the inside function. So now what we want to do is take a look at example. We're going to kind of switch things up a little bit. We're going to take a look at example 4, and then we're going to come back to the chain rule for powers. So this is the work that we did yesterday. And I'm going to make it a little bit larger so we can see it a little bit better. All right. So when we're looking at this part yesterday, what we did was we prepared a table where we took some different composed functions here that you see on the left, and we split them up into their inside function and their outside function. And so what I want us to do now is to actually compare and apply the formula. So we want to let u be the inside function, and we're going to let the outside function be u raised to whatever power or the sine of u or whatever it happens to be, and we're going to apply our formula. So the first thing we want to do if we're applying Leibniz's rule, so we're doing method 1, which is the more explicit of the two rules, is we take the derivative of the outside function. So we're going to start in column 2 over here, and we want to take the derivative of the outside functions. So the derivative of u to the 10th would be 10 times u to the 9th, right? And then we take the derivative of the inside function, which would be 3. So when we're done with the derivative of the inside function, we can find the derivative combined, which would be 3 times 10u to the 9th. And then we replace the u with what it was originally. So this gives us 30 times 3x plus 7 raised to the 9th power. All right. So that would be our final derivative. We take the product of the derivative of the outside with the inside plugged back inside of it times the derivative of the inside function. So that gives us 3 times 10u to the 9th. Then we replace the u with the 3x plus 7 again, and that gives us our result. Let's take a look at the next one down. For the next one, the derivative of the outside function would be cosine of u. When we take the derivative of the inside function, u is x divided by 4, or 1/4 x. You can also think of it as 1/4 x. So the derivative is 1/4. Move this over a little bit. And that means when I take the product, I get 1/4 cosine of u, which gives me 1/4 cosine of x over 4, since u was x divided by 4. All right, does everybody understand how I'm applying the rule? Okay, so we're taking the derivative of the outside function with respect to u, which is dy du, and then we're taking the derivative of the inside function with respect to x, which is du dx, and then we're multiplying the two together so that y prime is equal to dy du times du dx. Okay, what about the next one? We have secant of x, which when we replace the inside function becomes secant of u. Our inside function over here was e to the x because our formula was originally secant of e to the x. So we made u be e to the x. which you can think of it, these are secant of x or secant of u. We take the derivative of secant of u, and that gives us secant of u tangent of u. Pen stopped writing. And then we take the derivative of the inside function, which is e to the x. And remember, I said yesterday, the derivative of e to the x is e to the x. So when we take the derivative of that, we get e to the x secant of e to the x tangent of e to the x. So we multiply the two together, and then we back substitute for u and replace it with e to the x. So we get the product of the derivative of the inside function times the derivative of the outside function with the inside function substituted back in place of u. Right. The next one we're looking at is e to the negative x squared. So the outside function is e to the x or e to the u. The inside function is negative x squared because it's the power on the exponential. We take the derivative of the outside function with respect to u, which gives us e to the u again. And then over here, the derivative of negative x squared is negative 2x. So we take our product, negative 2x e to the u, which becomes negative 2x e to the negative x squared. So again, you're substituting the inside function back in place of u in the outside function's derivative, and then multiplying by the derivative of the inside function. The next one is a little bit more difficult. It's a little bit longer. We have the quantity x plus 2 to the 5th times the quantity 3x cubed plus 3x, all raised to the 4th power. The very last thing you do in the order of operations is the 4th power. So that becomes the outside function. So then our outside function is u to the 4th, and the inside function is the product of those two binomials, the first one raised to the 5th power. So the derivative of the outside function with respect to u is 4u cubed. And the derivative of the inside function, oh my, we may have to leave this one to later, because how would I take the derivative of the inside function? There's no way I have enough space here to do that. What would I need in order to take the derivative of the inside function?
The power
product rule.
I need the product rule, and I will need the chain rule again, because I've got inside of this x plus 2 to the 5th, I've got the composition of two functions again, x plus 2 on the inside and the 5th power on the outside. So let's go down to the space below and we'll work on this one down here. So the derivative of u with respect to x of this x plus 2 to the 5th times 3x cubed plus 3x, we'll think of this as f and this is g. So I need to take the derivative with respect to x of x plus 2 to the 5th power times g, which is 3x cubed plus 3x. And then the next thing I'm going to do is take g prime. So I can do the derivative of the second product, second factor, which is 9x squared plus 3 times the first one, which is x plus 2 to the 5th. All right. Now I need to take the derivative of this x plus 2 to the 5th, but this invokes the chain rule again. I have two functions. Inside is x plus 2, outside is 5. So I can think of this, we'll do another u. So this u is x plus 2, and this becomes u to the 5th. So I can think of this as 5u to the 4th, and the derivative of x plus 2 is 1. So this becomes 5 times x plus 2 to the 4th power times 1. All right. So when I do the derivative with respect to x, I get 5x plus 2 to the 4th power times 3x cubed plus 3x plus 9, oops, my parentheses went in the wrong place, 9x squared plus 3 times x plus 2 to the 5th. That's all my du dx. Now I need to multiply this by the outside function and substitute the inside function back in again. So I'm going to multiply this by 4u to the 3rd. So the derivative of y with respect to x is equal to 4 times x plus 2 to the 5th, 3x cubed plus 3x, all raised now to the 3rd, times another 5 times x plus 2 to the 4th, this is all in brackets, times 3x cubed plus 3x, plus 9x squared plus 3 times x plus 2 to the 5th. All right, so this one becomes quite long and quite complicated. We're doing the derivative of the outside function, which is 4u to the 3rd. So 4 frees the inside, same as the original, to the 3rd power, times the derivative of the inside. The derivative of the inside invokes the product rule, where we have derivative of another chain rule times the second times derivative of the first, or derivative of the second times the first. I think I did that right, didn't I? Yeah. All right. So this one is quite long. All right. However, it is an expression that represents the derivative, and it will give us the derivative correctly. And it's a lot easier, believe it or not, than multiplying this out 5 times and then multiplying it by this. Much easier than that. All right. And then raising the whole thing to the 4th power, because this would have to be raised to the 5th, then multiplied by that, then the whole thing multiplied by itself 4 times. Trying to do that without a mistake would be almost impossible. So even though this is complicated, it is in fact easier than the direct method. Okay, let's take a look at the next one, which is 5x squared plus 11x, all raised to the 20th power. So the outside function is the 20th power. The inside function is 5x squared plus 11x. So we replace the inside function and make it u, and that becomes u to the 20th. So now we take the derivative of the outside function, which is 20u to the 19th power. We're going to substitute the inside function, 5x squared plus 11x, back in place of u. And let's take the derivative of the inside function. The derivative of our inside function is going to be 10x plus 11. So we end up with 10x plus 11 in parentheses times 20 times 5x squared plus 11x raised to the 19th power. So we could move the 20 to the front. Then we have 10x plus 11. Then we have the 5x squared plus 11x, all raised to the 19th power. All right, right there. A little small, getting a little hard to write in there. The next one is also going to be more complicated because the inside function is a quotient. The denominator of the quotient has 2 terms, which means we can't get rid of the fraction. There's no way to split it up into multiple fractions. So we're going to have to do the quotient rule. There's no way around it. When we look at this outside function, it is something to the fifth power, so it becomes u to the fifth power. So this becomes 5u to the fourth. Now when we do the derivative of the inside, we can take the quotient rule. So du dx is going to be f prime g minus g prime f over g squared, which is going to be the derivative of the top, which is 3 times the denominator, 4x plus 2, minus the derivative of the denominator, which is 4, times the numerator, which is 3x, all divided by the denominator, 4x plus 2 quantity squared. Now we clean up the numerator, which would give us 12x plus 6 minus 12x. So the 12x's cancel. And we have 4x plus 2 quantity squared in the denominator, which gives us 6 over 4x plus 2 quantity squared. Then we can substitute this with our outside derivative, which is 5u to the fourth. So the derivative of y with respect to x is equal to the derivative of y with respect to u times the derivative of u with respect to x, which we said was 5 times the inside function unchanged, which is 3x over 4x plus 2, all raised to the fourth power. That's the derivative of the outside, freezing the inside function at what it was originally, times the derivative of the inside function, which is 6 over 4x plus 2 quantity squared. Now, there are some ways to simplify this a little bit and rewrite it in various forms. You can move the 6 and the 5 together. That would give you 30. You could split the power of 4 and put it on the 3x and on the 4x plus 2. That would give you 4 of the 4x plus 2 in the denominator plus 2 more, which would give you 6 total. So you could rewrite this one as 30 times 3x to the fourth power over 4x plus 2 quantity to the sixth, right? Which would be a relatively simple way to put it. There is a common factor in here of 2, which you could factor out. If you do factor it out, it becomes 2 to the sixth power because it's also raised to the sixth power. Okay. Are there any questions before we go on to the next problem about how we're doing Leibniz's notation method of the chain rule?
I just got lost in that last simplification.
In the last simplification?
Yeah.
Sure. So we have 5 times 6, and then I split the powers, 3x to the fourth over 4x plus 2 to the fourth times 4x plus 2 to the second. The bases are the same, right? They're both 4x plus 2. When the bases are the same, remember that you add the powers. So you add 4 plus 2, and that gives you the 6. Okay?
Yeah, got it. I just couldn't find the 30 in the top.
Oh, the 30.
Yeah,
From
that
the
I
5
found.
and the 6.
Yeah, good.
Okay. All right. Any other questions before we go on? Okay. Let's go and look then at the chain rule for powers, and we'll actually practice this method again. So don't worry about not having enough practice today. You'll get enough practice today and in the days to come, because the chain rule is pretty much a part of most problems. It's very unusual not to have the chain rule be a part of most equations. So it's something that you're going to be seeing an awful lot in the future. Okay. let's now take a look at the next part. Not sure what happened there. Okay. The chain rule for powers. When we're looking at the chain rule for powers, we're talking about the power rule that we applied multiple times on the previous one. So for example, if we had something like 3x minus 11 raised to the 5th power, the outside function is u to the 5th, right? So we can think of g of x here as being our inside function, which is 3x minus 11. Almost looks like an 8x minus 11. So g of x is what's on the inside of the power. Then the rule just becomes pull the power to the front, freeze the inside, reduce the power by 1, and multiply by the derivative. So the rule here would become for h prime of x, we would get 5. We would freeze the inside at 3x minus 11, raise that to the 4th, because this is the power rule. Pull the power to the front, reduce the power by 1, freeze the inside. And then we would multiply this by the derivative of 3x minus 11, which is 3. So this gives us what's called the chain rule for powers, which gives us the 5 times 3x minus 11 to the 4th times 3. The 5 and the 3 are both constants. This would become 15 times 3x minus 11 raised to the 4th power. Let's practice this again. First thing we want to do on this one, we want to find the derivative because we're looking for the tangent line equation at a particular point at x equal -2. So we need 2 pieces of information. We need a point on the original function, and then we need the slope of the tangent line from the derivative. So remember, the point comes from the original function, not the derivative, but the slope of the tangent line comes from the derivative. So when we're looking at this one, we're going to need a point. And so far, what we know is that the x coordinate is -2. So we take our -2 and we plug it into the original function, which gives us -2 squared minus 2 inside parentheses, all of it cubed. This gives us 4 minus 2 in parentheses cubed, which gives us 2 cubed, which is 8. So our point is -2, 8. And notice we did again use the original function, not the derivative, to find the point. Now we want to find the derivative so we can find the slope of the tangent line. So now we're going to apply the derivative formula using the chain rule for powers. So we have x squared minus 2 quantity to the 3rd. So the outside function is going to be u to the 3rd power, and the inside function is the thing being raised to the 3rd power, which is x squared minus 2. So the derivative of the outside with respect to u is 3u to the 4th. The derivative of the inside, x squared minus 2, with respect to x is 2x. Putting this together, we get the 3 times freeze the inside, x squared minus 2 to the power of 2. Why did I have a 4 here? I'm looking at that going, something's wrong. Okay, 3u squared. All right, so this gives us reduce the power by 1, not increase the power. I'm integrating already. Okay, so this gives us 3, freeze the inside, reduce the power by 1 times derivative of the inside, which is 2x. So f prime of x, when we combine our constants, is 6x times x squared minus 2, the quantity squared. All right. Now, this is a formula for the derivative at any point, but we need the derivative at -2. So the next thing we're going to do is plug in the -2 so we can find the derivative at that point. And that will give us the slope of the tangent line at the point -2, 8. So when we substitute, we get a -12 times 4 minus 2 squared, which gives us -12 times 2 squared, which is -12 times 4, which is a -48, right? So we have the point -2, 8, and the slope of the tangent line is -48. Now we take point slope form of a line. Y minus y1 equals m tangent x minus x1, and we write the equation of the line. Y minus 8 equals -48, x minus a -2. The double negative will make it an x plus 2. And you could leave it in that form if you want to. Let me catch up to where we are in the notes. Okay. All right.
So I have a question about what areas we're pulling information from for, I want to say like the second to last step where you drew
Okay.
the bracket on the two derivatives. So we said the outside function was u to the third, and then we go over to the derivative.
Did I mess up the derivative? What was it again?
Or maybe I miswrote it. I don't know.
No, the original function is x squared minus 2 to the third. So the
Right.
original is u to the third. So when we take the derivative, we get 3u squared.
Okay.
And then the derivative of the inside function, which is x squared minus 2, becomes 2x. So to put these two together and multiply, we take the outside function 3 times u squared, and we replace u with the inside function again, x squared minus 2.
Okay.
Okay.
Thank you.
Yep. So we've already done number 4. We want to talk now about incorporating the chain rule into the derivative rules. This is a better way to memorize the derivative rules. There are, of course, the derivative rules that we've already learned: the derivative of a sum, the derivative of a difference, the derivative of a product, the derivative of a quotient, the derivative of a constant times a function, the power rule, and the trig derivatives. So we've already learned quite a few. What we would like to do is incorporate the chain rule into those derivative formulas so that when you memorize them, the chain rule is already built in. These are called the U form of the derivative rules, and you'll find these on D2L in Professor D's material. There is a section under the Calculus 1 material that talks about derivatives, and in there you'll find a U form for the derivatives. All right, there's a handout in there on the U form for derivatives. And these are the ones that you'll find in there. So here are the rules with the chain rule built in for the trig functions. All right, see if I can get them all on there at the same time. So when we take the derivative of sine, and we're thinking of the inside function as possibly being another function, this becomes derivative of the outside which is derivative of sine, which becomes cosine. And then the cosine gets multiplied by the derivative of the inside. So this form of it, this cosine of u du dx, is actually the derivative of sine with the chain rule already built into it. So when you go to memorize the derivative of sine, you want to memorize this formula, cosine of u du dx. When you take the derivative of cosine, you get negative sine. And then depending on what u is, you also do du dx. Now, if u was just x, it still works because the derivative of x is just 1. So we would be multiplying negative sine of x times 1, which is still negative sine of x. So the formula works no matter what and is a better way of thinking about the rules. Okay. All right. Now, what about tangent? Tangent's another important one that we study. The derivative of tangent is normally secant squared. So all the chain rule adds into it is the derivative of the inside function du dx. So this du dx represents derivative of the inside function. So these are the rules with the chain rule already built into it. And here are some of the other rules that we've learned this semester as well. These are the ones that you need to have committed to memory. So we have the derivative of a constant, which is 0. If I give you the derivative of pi, hopefully you know to give me 0. If I say something like the derivative with respect to x of pi, pi is just a constant, so you should come up with 0. The derivative of a constant times u is c times the derivative of u with respect to x. And then if you have two functions added together, this just gives you the derivative of each one added together, or if they're subtracted, they're subtracted. This is the product rule up here. It looks a little different from the way that you've memorized it, but it is the same product rule. All right, so this is your f prime g plus g prime f. All right, so that's basically what you have up there. And then the next one down is the quotient rule. And this is your f prime g minus g prime f over g squared. All right, but it has the chain rule built into it. Okay, and then the last one is the power rule, which we call the chain rule for powers, which is n u to the n minus 1 times the derivative of u with respect to x. I want to add one more to this list of things for you to memorize, and that's going to be this one. We want to do the derivative with respect to x of the square root of u. I like to add this one because the square root of u shows up a lot. And if it's one that you have memorized, it just makes your life go a lot faster and it's a lot simpler. So let's think about how we might actually find the derivative of that. So if we're thinking about the derivative of the square root of something, and again, the u could be anything. It could be the quantity 3x plus 2. It could be x squared minus 2x plus 5. It could even be sine x plus 3. It's anything, all right? U represents any other function. We can write this as u to the 1/2 power and then take the derivative of that. Remember, the 1/2 power represents the square root. Fractional exponents are actually roots. And the denominator tells you what kind of radical it is. And the numerator is the power like it normally is. So we can think of this as the derivative of u to the 1/2. And then we can apply the power rule, which is over here on the side. So applying the power rule, we bring the 1/2 to the front. We reduce the power on u by 1, which makes it a negative 1/2. And then we multiply, of course,
by the derivative of u with respect to x. All right. And that's basically using this rule right here. Now, to rewrite it in a better form, though, notice that we have a negative exponent, and the negative exponent will send just that factor to the denominator. So it doesn't affect the 1/2, and it doesn't affect the du dx, but it sends the u to the 1/2 to the denominator. And now the power on it is a positive 1/2 because we moved positions. It's still being multiplied by du dx. And the last thing we can do is we can back substitute. Instead of writing it as u to the 1/2, we can back substitute and write it as the square root of u again, so that this becomes 1/2 the square root of u du dx. And this is the form I'd like you to memorize. 1/2 the square root of u du dx. So the derivative of a square root is 1/2 the square root du dx, where du dx represents the derivative of the inside function for the chain rule. All right. Okay. Let's now look at some more examples. Here's an example here. And I actually want to show you a couple of ways of solving this problem. We'll do it two ways. We're going to do it first with the quotient rule, and then we'll do it with the product rule, because actually it can be done either way. There is no quotient rule that cannot be turned into a product rule. Let me say that again. There's no quotient rule that cannot be turned into the product rule. And I have had some students who really loathed the quotient rule. So they just turned every quotient into a product, and then they never had to deal with it, which is fine. You can do that. All right. You do whatever makes the most sense to you and works the best. So we're going to approach this as a quotient at first. We're going to think of the numerator as f and the denominator as g. So h prime of x is going to be f prime g minus g prime f over g squared. Remember, when you're doing the quotient rule, that you get subtraction in the numerator. All right. The next thing that we want to do is apply the formula. So we're going to come over here. We have h prime of x equal to derivative of the numerator is 1 times the denominator 2x plus 3 quantity cubed minus. Now we need the derivative of the denominator. And now what we're going to practice is we're going to practice the in place all in one form of the chain rule. We're going to do the chain rule in one fell swoop. So the outside function is u to the third. The inside function is 2x plus 3. So when we think of the outside function, we're going to think about something to the third power. So the derivative of it would be 3 times the something to the second power. All right. Now the something is going to be frozen at the original inside, which is 2x plus 3. This part right here represents the derivative of the outside function. Now we want to take the derivative of the inside function. The derivative of 2x plus 3 is 2. So all of this represents g prime. All right. So we have derivative of the outside function with the inside function frozen times derivative of the inside. Then we multiply it by f, which is x, which is the numerator, all divided by the denominator squared. So we have 2x plus 3 quantity cubed, and then we want to square it. Now, when you square a cube, you have one base and 2 powers. So the exponent rule tells you to multiply those 2 powers together. When you multiply the 2 powers together, you get the 6th power. 3 times 2 gives you 6. All right, when you have two powers in one base, you multiply. When each has its own base and you're multiplying, you add. So this becomes 2x plus 3 to the third power minus, now you kind of have to pick out the single factors, single term factors, 3, 2, and x. So 3 times 2 is 6, times x gives me 6x. And then I've got a 2x plus 3 quantity squared, all divided by 2x plus 3 quantity to the 6th. Now, web work will probably expect you to reduce this a little bit. So what you're looking for is a common factor. The only factor you have in the denominator is the inside function 2x plus 3. Notice that it is a common factor out of the terms in the numerator. You have two terms in the numerator, the quantity cubed, and the second one, negative 6x times the quantity squared. You have two terms, and 2x plus 3 is a common factor of both. So we're going to factor out the 2x plus 3, and we have at least two of them in each term in the numerator. So when I factor it out, this leaves behind one set of 2x plus 3 from the first term and minus 6x from the second term. And then this is all divided by 2x plus 3 quantity to the 6th. All right, the next thing you want to do is you want to reduce. Now that you have buried your addition and subtraction all in parentheses, you can reduce. I have 2 of the factors on top and 6 on bottom. So that cancels 2 of the ones in the denominator and leaves me with 4 in the denominator. So that leaves me with 2x plus 3 quantity to the 4th. The numerator leaves me with the 2x plus 3 minus 6x, which I don't have a power on the 2x plus 3 other than 1. So I can drop the parentheses. 2x minus 6x gives me a minus 4x. So I have a minus 4x plus 3. And this is my final answer right there. Right? Now, I said there's more than one way to do this one, so let's take a look at another way of doing the same problem, but with the product rule instead.
Before we jump into that, could we look at G prime again in numerator?
Yes. All right.
So I was following until we got to the 2 on the right side, and then I don't know where the X came from.
Ah, okay. So this part right here is G prime, and this one's F.
Okay, thank you.
Okay, so this is derivative of the denominator, derivative of the outside, freeze the inside, times derivative of the inside, and then times the numerator, which was X. This is from our G prime F formula.
Thank you.
Yep. Okay, let's try this problem again. And this time we want to turn it into a product rule. So looking at the original problem, which is right here, how could I turn this into a product rule? What could I do that would make this into a product instead of a quotient?
Use 2 fractions, like x.
I hadn't thought of that. That is a good idea. You're right. I could use 2 fractions, but that might make it worse. How could I get rid of the fraction and just have products?
Can't you just
Normally,
raise
I wanna-
2x? Can't you just raise 2x plus 3 to the negative third?
Good. So Hannon is suggesting that we take the factor that's in the denominator and we rewrite the power with a negative exponent, which would lift it to the numerator. So this is another way of rewriting the same problem. So we have x times 2x plus 3 raised to the negative 3 power. This turns a quotient into a product. All right. Now that it's a product, we can do the product rule. So when we're looking at h prime of x for this form of it, we would have f prime g plus g prime f. Remember when you're doing the product rule that you get a plus, and when you're doing the quotient rule, it has a minus in it. So now we're going to do the product rule. F prime is the derivative of x, which is just 1. So we have h prime of x, which is equal to 1, times the derivative of the second part, which is 2x plus 3 to the negative 3, plus, now we have to take the derivative of the second factor, which is this 2x plus 3 to the negative 3. Now the power for the chain rule for powers is the same, even if it's a negative exponent. So we bring the negative exponent to the front. We get a negative 3, freeze the inside at 2x plus 3, reduce the power by 1, so it goes to a 4, and then multiply by the derivative of the inside, which is 2. So all of this represents g prime. All right. And then we're going to multiply by f, which is x. All right. So we're applying the product rule, and this is the chain rule inside of the product rule. Now, the next thing we want to do is go ahead and clean things up a little bit, combine any single term factors, and move all of the factors with negative exponents back into the denominator where they normally would be. So this becomes 1 over 2x plus 3 quantity cubed minus 6x over 2x plus 3 quantity to the 4th. So the 6x comes from the 3 times 2 times x, and it has a negative on it from the original negative 3 power. So it becomes minus 6x over this to the 4th. Now, in order to combine these, I have to have a common denominator, which is going to be the larger power, 2x plus 3 to the 4th. So I want to multiply the first set by 2x plus 3 over 2x plus 3. So I'm going to multiply by 2x plus 3 over 2x plus 3. That's a form of 1. And that will give me the common denominator, 2x plus 3 over 4. So this gives me 2x plus 3 over 2x plus 3 to the 4th minus 6x over 2x plus 3 to the 4th. And when I combine the common fractions, I get negative 4x plus 3 over 2x plus 3 to the 4th. Now, I don't know which one of these makes more sense to you or which one seems easier, whichever one seems easier to you or more logical, that's probably the way your brain works. So that's the way you should do it. Okay, now we want to switch and take a look at things that have composites of 3 or more. As awful as this sounds, it is not uncommon to have composites of 3 or more different types of functions together. So when we do this, we'll have multiple levels of composition, which means that when we take the derivative, we have multiple applications of the chain rule within the same factor or within the same term. So we want to take a look, for example, at this one right here, where we have k of x equal to h of f of g of x. And you'll notice that I've made my parentheses different sizes to emphasize which one is inside which one. G is inside of f in place of the variable x. f has gone inside of h in place of the variable x. So we've got what we call nested or layered composition. All right. So let me give you an example of a nested composition problem. Sine of 2x minus 3 to the 11th. Okay, this is a nested composition problem. What different functions do we see? Which one is h, which one is f, and which one is g? The order of operations will help you figure out which one is on the very outside and which one's on the very inside. If I said x equals 1, what would you plug it into first? 2x minus 3. That means that 2x minus 3 is the innermost function, and it must be the g. All right. So 2x minus 3 must be our g function, because it's the very innermost one, the place where we would substitute a value first. After I had 2x minus 3, the next thing I would do would be what? Would I raise it to the 11th or take the sign of it? What would happen next in the order of operations?
Raise it to the 11th.
Yes, Michael's correct. We would raise it to the 11th power. And because I would do that next, that means the next layer, or f of x, is equal to u to the 11th power. And then the last thing I would do would be to take the sign of it. The last thing you do becomes the outermost function, in this case, h. So h becomes the sine of u, where our u's are different u's. So maybe we should call this one w or something like that. All right, so we've got u to the 11th and a sine of w. All right, so we have nested or layered composition going on here. How would we find the derivative of something like sine of 2x minus 3 to the 11th? Well, we pull it apart the same way you have to pull apart an onion. To get an onion pulled apart, you have to pull apart the outer layers first. So we attack the outermost layer, which is the outside function, which is sine. So we would take the derivative of sine, which is cosine, and then we would freeze the inside. The original inside was 2x minus 3 raised to the 11th power. We freeze that. We don't change what was inside of sine, stays inside the derivative of sine, which is cosine. Let me say that again. What was inside sine stays inside the derivative of sine, which is cosine. Now we multiply by the derivative of what was inside. So now we're focused on the 2x minus 3 to the 11th. The next layer is the 11th power. So the next thing we do is take the derivative of the 11th power, which is 11 times something to the 10th power. We freeze the inside of what was inside the 11th power, which was 2x minus 3. So what was inside the 11th power stays inside. And we have the derivative of the 11th power, which is 11 times something to the 10th power. And then we take the derivative of the inside function, 2x minus 3. The derivative of 2x minus 3 is 2, and there's nothing else inside of it. We've reached the innermost layer of the onion, or the innermost layer of the problem, and so we're done. All right. And then the last thing that we would do, of course, would be to clean this up. Because I have cosine, which has an argument to it, it will probably go at the back. I would combine the 11 and the 2 and write that as 22. So this would become 22, 2x minus 3 to the 10th power times the cosine of 2x minus 3 raised to the 11th power. This would be the derivative of that 3-layer deep nested composition function. And this is what it looks like when you write it out in terms of the chain rule. Derivative of the outermost layer, H prime, leave its inside alone, f of g of x. Then the derivative of the next layer, which is f prime, leave its inside alone, g of x. Then the derivative of the inside of the previous one, g prime of x. And that gives us our nested derivative. In other words, you get a string of factors that are going to be multiplied together. The thing you want to remember is that you're taking the derivative of each layer at a time, freezing the old inside, and then multiplying by the derivative of the inside. Okay, let's take a look at some examples of these multi-composition functions. We've got sine to the 6th power of x cubed. Now, we write the 6th power between the trig function and the argument to it, but keep in mind that this means exactly the same thing as writing the sine of x cubed, the whole thing raised to the 6th power. And in this form, the second form, it's a little more obvious that the 6th power happens after the sine happens. So that sine is happening before the 6th power. Because the 6th power is the last thing to be done, it's the outermost layer, all right? So we can think of the innermost layer. I think I called it g of x before, as x cubed. The second layer, which I believe before we called f of x, is the sine of u. And the third layer, or the outermost one, is what we called h of x, which is w to the 6th, all right? Something to the 6th power. So I have three functions here: something cubed, the sine of something, and something to the 6th. So what we want to do then is we're going to apply the rules going from the outside to the inside, like you peel an onion. I feel like I'm talking about, what was the movie with Mike Myers? Oh my gosh.
A classic Shrek.
Shrek, of course. It's like an onion, right? Ogres are like onions. So the chain rule is like an ogre, like an onion. You've got to peel from the outside in. So we're going to start here, and h prime is going to be 6 something to the 5th power, freeze the inside. What was inside the 6th power was the sine of x cubed. That's frozen. Now we're going to multiply by the derivative of what was inside there. The next layer is sine. What's the derivative of sine? Cosine. What's inside the cosine should be exactly what was inside sine. That won't change. It stays x cubed. Then we multiply by the derivative of what was inside cosine. So each time we take the derivative of the outside, we freeze the inside, and then we multiply by the derivative of the inside. All right? So the derivative of x cubed gives us 3x squared. Now we're going to locate our single factors. We have a 6 and a 3, which will give us an 18. We also have an x squared, so I'm going to have an 18x squared. And then we could write sine of x cubed to the 5th, cosine of x cubed. Or you can use the other notation for the 5th power, and you can write 18x squared sine to the 5th of x cubed, cosine of x cubed. If you're going to write two trig functions side by side, be sure that you put parentheses around the arguments. That stops the last part from becoming a part of the previous argument. So when you write two trig functions side by side, make sure that you do put parentheses around the arguments. This is one time when they're really not optional. Let's take a look at another one. We have sine of cosine of 7x. So let me give you a minute and try to decompose this one on your own. What is the innermost layer? What's the second layer? What's the third layer? You should have gotten 7x as the innermost layer, cosine of u as the second layer, and sine of w as the outermost layer. Now take the derivative and let's compare answers. Okay, so when we're doing this one, the outermost layer is sine. The derivative of sine is cosine. Leave the inside alone. The inside of sine was cosine of 7x, so it should still be cosine of 7x. Then we take the derivative of the inside, cosine of 7x. Derivative of cosine is negative sine. Freeze what was inside cosine, that was 7x. It should still be 7x. Then we take the derivative of this inside, derivative of 7x is 7, so we get a 7 here. There's nothing inside the 7x, so we're stuck. Then we can pull the negative and the 7 to the front. I would probably put the sine of 7x next, and then the cosine of 7x goes at the back. The reason is this is actually a trig function inside of a trig function. We still have a composition in our derivative, but that's okay. We've taken care of the derivative using the chain rule, and we still have a composition. Let's take a look at the next one, which is this one right here, and let's decompose it and then find the rest of it. See if I can get it pop up. All right. This one is a lot trickier. On the inside, we have actually a sum. Which is 6 plus the secant of pi x squared. This time, it's not a composition within a composition. It's a sum in a composition. And within the sum, a part of the sum is also a composition. Not the whole thing, but just one part of it. Secant has an inside function, and inside secant is pi of x squared. So this is not quite like an onion. This is more like an onion with two centers in it. All right. So what are we going to do? We also have this square root here, and then we have inside secant. We have pi x squared. And the outermost, I'm not sure why that is coming up highlighted, is the square root. All right. So the first thing we have to pull off is the square root. It's the last thing that would be done in the order of operations. So remember that we're going to memorize the formula for a square root as 1 over 2 the square root du dx. So the derivative of h prime becomes 1 over 2 the square root of something times derivative of what was under the square root. So derivative of square root, 1 over 2 the square root. We freeze the inside of what was under the radical, so it stays 6 plus secant of pi x squared times. Now for the next part, what we need to do is take the derivative of 6 plus secant of pi x squared. When we do this, this is a sum. The derivative of 6 is 0. So up here, this is going to be the derivative of the sum. So this is going to be 0 plus, what's the derivative of secant? The derivative of secant is secant tangent. We freeze its inside, so it stays pi x squared. And then we have to multiply the secant part by the derivative of what was inside secant. What was inside secant was pi x squared, and the derivative of that would be 2 pi x. Right?
Wouldn't it be pi will turn 0? Or
Pi is a constant, right? So
Right.
it's the same as like 3x squared, right? So it's going to be
oh,
times
okay.
pi times x. Remember that pi is not a variable, so you do not apply the power rule to pi, all right? You do not apply the power rule or the product rule with pi. Pi is just a number. It's a special number, but it's still just a constant. Okay, so cleaning this one up, I would move the 2 pi x to the front. So I have 2 pi x secant of pi x squared, tangent of pi x squared, all divided by 2, the square root of 6 plus secant of pi x squared. And then what could I do with the 2's? I could cancel the 2's. That would be the only thing I could do. Those 2 would cancel. I can't cancel anything else. I can't take the radical, even though I've got an x squared in here, because 1, it's inside secant, and 2, it's inside of a sum. You're not allowed to split radicals across addition or subtraction. You can only split across multiplication and division. This one is a more challenging problem because it's not a function within a function within a function. It's a function within a function, and then only part of the inside function is nested. The other part is just regular. The 6 is just a regular part. Okay, let's take a look at example 9.
Professor D,
Yes.
I think the question Juan was asking was, since pi is a constant and the derivative of a constant is 0, wouldn't that pi be 0?
Wouldn't that pi be 0? When
And
you're
the
looking at
pi
pi x squared and you're taking the derivative of this, you get 2 pi x.
But isn't the pi a constant? So wouldn't that be
It
0?
is a constant. If you took the derivative of 3x squared, what would you get?
6x.
But you wouldn't get 0.
Okay.
Does that make sense?
Yeah.
I'm just applying the power rule. The pi is a constant which can be pulled out and using the scalar multiple property. So this doesn't affect it. Just think of it as like 3.14. So I'm multiplying 2 by about 3.14 times x. All right.
Okay.
Otherwise, I would have to apply the product rule. And if I did the product rule, then yes, the derivative of pi would be 0.
Okay.
Does that make sense?
If
Yeah.
pi was just by itself, then
If
it
it
would be
was-
considered a
Then it
constant.
would be 0. Yes. If I did the derivative of pi, that's 0. And I can also do the derivative of, and maybe I should write this out so you can see it, using the product rule. The derivative of pi is 0 times x squared plus 2x times pi, which gives me 0 plus 2 pi x. Okay, does that make sense? Hopefully I've cleared up that confusion now. The derivative of pi by itself as a constant is 0, but pi multiplied by x is a constant factor, a scalar. All right, so it just tags along. Okay, let's take a look now at example 9. We have 2 examples left to do, 9 and 10, which are applied problems. In example 9, we have a position of a freight train given by a function. S of t is 100 times t plus 1 to the negative 2. It's really a quotient in disguise, with s in meters and time in seconds. At t equals 6 seconds, find the train's velocity and its acceleration. And then using that information, at 6 seconds, is it speeding up or slowing down? So at 6 seconds, we want to find the velocity and the acceleration. So remember, v of t is the derivative of the position function. So velocity is going to be the derivative of position, which means that I can take the derivative of this using the chain rule for powers. So this is going to be the negative 2 power on the outside times 100, and on the inside, t plus 1. So I pull the negative 2 to the front. So I get a negative 2 times 100, freeze the inside, it stays t plus 1, reduce the power by 1, so it becomes a negative 3, and then multiply by the derivative of the inside. So this is method 2, where we're doing it all in one step, sort of in our head. Derivative of the outside function, pull the negative 2 to the front, freeze the inside, reduce the power by 1, multiply by the derivative of t plus 1, which is 1. All right. Cleaning this up a little bit, this would give me negative 200. And then I can drop the t plus 1 to the third to the denominator. Notice that the negative 200 stays in the numerator because the power on it is 1. It is not negative 3, it's 1. Yes, it's multiplied by that expression raised to the negative 3 power, but it's not a part of it. And it has its own power. The power on negative 2 is 1, the power on 100 is 1. So they stay in the numerator. Now, what would the velocity be at 6? So now we can find v of 6 by plugging in 6 to this expression. And we get negative 200 over 6 plus 1 to the third, which is 7 to the third. So this is negative 200 over 7 to the third, which I don't know exactly what it comes out to be, but it is negative. All right. Okay. Now let's find the acceleration. So that was part A. Now let's do part B. Acceleration is the derivative of velocity, and it's the second derivative of position. So it's s double prime. Now I can write this using this first one. I can take the derivative again. This is basically negative 200 t plus 1 to the negative 3. So I can pull the negative 3 to the front. So this becomes negative 3 times negative 200 times freeze the inside and reduce the power by 1 times derivative of the inside. So I've taken the derivative of the derivative, where I'm thinking of this as negative 200 t plus 1 to the negative 3. So I pull the power negative 3 to the front, multiply it by the negative 200, freeze the inside at t plus 1, reduce the power by 1 to negative 4, and multiply by the derivative of t plus 1, which gives me 1. Right? So negative 3 times negative 200 is going to give me a positive 600. And this is going to give me 600 t plus 1 to the negative 4, or 600 over t plus 1 to the 4th. Now, what does this come out to be at 6 seconds? So at 6 seconds, when I plug this in, I get 600 over 7 to the 4th, which is positive. Now on your homework for 3-4, 3-5, maybe it was 3-5, I can't remember which, one of those, you're asked to determine whether something is speeding up or slowing down. one of the ways we discussed finding out whether something's speeding up or slowing down is by looking at the sign of the velocity and the sign of the acceleration. If they're both the same sign, it's speeding up. That means if they're both positive or both negative, it's speeding up. The only time it's slowing down is when one of them is positive and the other one is negative. So if velocity is positive and acceleration is negative, it's slowing down. If velocity is negative and acceleration is positive, it's slowing down. When they have the same sign, it's speeding up. So in this case, we can decide that because the velocity is negative and the acceleration is positive, it is definitely slowing down. And that's because they have opposite signs.
I have a question.
Yes.
In some Weber questions, they ask this, but they ask for the intervals.
Yes.
How can we get the intervals of when it's slowing down or when it's
Okay,
speeding up?
these two don't have any because they're pretty much always one or always the other. Does everybody see that? This function up here for velocity, -200 over t plus 1 cubed, time is always positive. So a positive plus 1 cubed is always positive, and then the negative makes it always negative. Likewise, the acceleration is always positive. The 600 is always positive, and anything to the 4th power is always positive. So here, you can't tell. But let me give you an example. I'll make up one. So this would be a different type of problem. Let's say that your V of t came out to be I'm thinking, bear with me a second here. T squared minus 5t plus 6. Okay. All right, so that's your velocity. Then if you were to factor it, you would get t minus 3 and t minus 2, right? So you get t equals 3 and t equals 2. That's if it equals 0. So that tells you when the velocity is 0, or in other words, where it is stopped. Okay, so the question is, if it's stopped there, then how do you know where it's accelerating and where it's not accelerating? How do you know how to determine the next part? So when we're looking at this, we know that the velocity would be stopped at t equal 2 and t equal 3. The question is, on either side of 2 and 3, what's the velocity doing? Remember, time starts at 0. So this is our time axis. And over here somewhere, I have a 2. And here I have a 3. So I'm going to put my velocity signs up here. All right. So let's take a test value like, I don't know, something on the left side of 2, like 1. All right. And let's plug 1 into the velocity equation. You can either plug it into the original trinomial or you can plug it into the binomial where they're factored. I find it easier to plug it into the binomial where they're factored because all I really care about is not the value, not the number, but the sign. Is it positive or is it negative? I need to know, is the velocity positive or negative? So when t equals 1, 1 minus 3 would be negative. 1 minus 2 would be negative. So I have a negative times a negative, which would make it positive. So at 1, it would be positive. So my velocity is positive here. All right. So when t equals 1, I get a negative times a negative, which equals a positive. All right. Now let's try another test value. We're cutting up the t-axis into 3 regions, below 2, between 2 and 3, and above 3. We need to look at each of the intervals between where it's stopped and where time is 0. So now I'm going to try t equal 2.5. When t equals 2.5, what happens? Well, 2.5 minus 3 would still be negative, just a little bit, but negative is negative. But 2.5 minus 2, that would be positive. So I have a negative times a positive, which gives me a negative. So I know in here it would be a negative value, which means that it's headed north here and headed south here. I don't know which side of the origin it's on because that's position, but I know it's headed north here and headed south here. What about here? Well, I'm going to try another test point, which would be when t equals, I don't know, let's say 4, because that would be a value up here. These are my primary points right here, 2 and 3, where the velocity is 0. So now I'm going to try when t equals 4. When I'm looking at when t equals 4, I get a positive and a positive times a positive is still positive. So it's positive again. Now this is the velocity. Let's repeat this process for the acceleration. If the velocity is t squared minus 5t plus 6, what is the acceleration function going to be? What is a of t?
2t minus 5.
2t minus 5.
Yep.
Okay, so I took the derivative and I get a of t is equal to 2t minus 5. Where is it 0? This would be an inflection point. This is where you pull your foot off the gas pedal, but you haven't put it on the brake, or you pull it off the brake, but you haven't put it on the gas pedal. This is where you're coasting in the car. You're not speeding up, you're not slowing down. Your acceleration is 0. You're not braking, you're not putting your foot on the gas pedal. I can't say accelerating because that's not what it means. All right, so this is the inflection point. So 2t minus 5 equal to 0 would happen when t is equal to 5 halves. All right, everybody buy that? All right, at 2.5. Okay, so now I'm going to add 2.5 on here. That means I need to go back and split up my velocity on either side. Now the velocity maintains over that whole interval, so it's negative on both sides of 2.5 because it's negative between 2 and 3. Now I want to know about the acceleration. I want to know what the sign of the acceleration is, and I'm going to put those up here in blue. So I'm going to do my test points. Now the acceleration only hits 0 at 2.5. And we know from the intermediate value theorem that the only time it can change from a positive to a negative, because it's a continuous function, is on either side of that 0. So I only have to split it into 2 regions. I've got left of 2.5 and right of 2.5. It can only change sign where it crosses the t-axis, all right? So I'm going to take a test point on the left, probably 1, and plug it into the acceleration equation. When t equals 1, I get 2 times 1 minus 5, which is a negative 3. So my acceleration is negative over here until I get to 2.5. What about on the other side? You could use 3 as a test point, or you can use 4 as a test point, anything above 2.5. So I'm going to use 3. 2 times 3 minus 5 gives me 1, which means that it is positive up here and up here. All right. Now to decide what intervals that it's speeding up and slowing down, I look to see where they have the same sign, speeding up, and where they have opposite sign, slowing down. So for example, if I were looking at this one, I would say it was slowing down over the interval from 0 until 2. Notice that at 2, they switch signs on the velocity. But between 0 and 1 and 1 and 2, they have opposite signs. One's negative and one's positive. So from 0 to 2, it is slowing down. when they have the same sign, both negative here between 2 and 2.5, it's speeding up. So between 2 and 2.5, it's speeding up, or 2 and 5/2, whichever way you want to write it. And then they have opposite signs again between 2.5 and 3, which means it's slowing down again. And then once it gets to 3, above 3, they have the same sign. They're both positive, so they're speeding up again from 3 to infinity. Right? Does this explain how to find the two? Make it a little
Yeah.
clearer? Okay.
Totally.
Okay, good. So Shuri's happy about this too. So this will help you on the homework figure out where the intervals are that you're speeding up and where you're slowing down. All right. I think we have one example left. This is sort of like a related rates problem. And I would put the related rates section, which is 4.1, in the top 5 most important and most difficult sections of this semester. So it's up there with 2.5. It's not as bad as 2.5. It is difficult though, all right? Chain rule is more important by leaps and bounds. Chain rule is vastly more important, but it is still important because it's an application section. So this is how the math gets used in the real world. The formula for the area of the circle is A equals pi r squared, where we know that r is the radius of the circle. Suppose the circle is getting bigger. So imagine, for example, an oil spill on the ocean. If they have an oil spill on the ocean, it starts out right around the tanker ship, and then it starts spreading out from the tanker ship, and the circle gets larger and larger, right, as time goes on. So the circle is expanding. So think of this as an oil spill on the ocean. It's coming out in the shape of a circle. This means that both the area A and the radius are getting larger. So you have your boat right here. This is my all-purpose vehicle, and it spills oil. So it starts out in a small circle around the boat, but at a later time, that circle has expanded, all right? The area is larger, but not just the area. The radius is also larger. Both of them are getting larger. We want to suppose the radius is given by the formula 2 minus 100 over the quantity t plus 7 squared, time in seconds. We're going to use the chain rule to find the rate. That's why this is called a related rate at which the area is expanding. All right. And then we want to find the rate at which the area is expanding at 4 seconds. Okay. So when we're looking at this one, we have pi r squared, which is our area, which is pi times 2 minus 100 over t plus 7 quantity squared. All right. So the formula is pi r squared, but r is this t minus 100 over t plus 7 quantity squared. So I replace the r with this formula, and then I square it for the formula pi r squared. Okay. Now I want to know the rate at which the area is changing. If the area is changing with respect to time, we call that dA dt. dA dt represents a change in the area with respect to a change in the time. So the actual notation tells you what the rate is doing. This is the change in area with respect to the change in time. The word rate typically means you have 2 different units in a fraction, one in the numerator, one in the denominator. So we'll have units for area in the numerator and units for time in the denominator, and that makes it a rate. Okay, so to find the formula, we need to take the derivative. Remember that pi is a constant, just like a phi. So it is not going to affect the derivative. It's just going to come along as a scalar multiple. So we pull the power 2 to the front and multiply it by the pi. So this gives us 2 times the pi, freeze the inside, 2 minus 100 over t plus 7 quantity squared, reduce the power by 1 to 1, and then multiply by the derivative of what's inside. Now, the derivative of what was inside was 2 minus 100 over t plus 7 quantity squared. So we can think of this 2 minus 100 over t plus 7 quantity squared. We can also think of this as 2 minus 100 times t plus 7 to the negative 2. If we think of it like that, then taking the derivative is simpler and we can do chain rule again. So when we take the derivative of the inside, the derivative of the 2 is 0. When we take the derivative of the second term, we get a negative 2 to the front multiplied by a negative 100. So we've got 0 plus negative 2 times the negative 100 times t plus 7, reduce the power by 1 to negative 3, and then multiply by the derivative of the inside. The inside function there is t plus 7, and the derivative of t is 1, and the derivative of 7 is 0. So we get a 1. The derivative of a t plus 7 is just 1. Now we need to clean this up a little bit and see if we can get it in a slightly better format. So we have 2t, or 2 pi rather, times 2 minus 100 over t plus 7 quantity squared times, we had a negative 2 times a negative 100, which is 200. And then we can drop the t plus 7 to the negative 3 to the denominator. So it becomes t plus 7 quantity cubed, like that. Now we could go ahead and distribute this out a little bit more. We could multiply the 2 by pi by the 200, and that would give us 400 pi over t plus 7 cubed times 2 minus 100 over t plus 7 quantity squared. All right. So it looks like that. Now, you could do some more algebra and you could get a common denominator, and you could probably combine this and get a little bit more cancellation, a little bit more simplification, but it's probably simple enough. It actually does simplify quite a bit more. If you want to try working on that, it does simplify quite a bit more. We can now actually find the second part though, which is what is the rate of change of the area at 4 seconds by plugging in 4. So this would be in, did it say feet or miles? Or did I even say? It's something per second. It's probably feet per second. All right. So this is changing.
I think it said inches, actually.
Oh, did it say inches? Okay. So this is going to be when t is equal to 4 seconds. So this would be 400 pi over 11 to the third times 2 minus 100 over 11 squared, right? Whatever that comes out to be. And I'm out of time, so I'm going to stop right here and leave you to figure out the rest of the algebra on your own. But hopefully this makes sense to you. The chain rule does. We've done some really difficult chain rule problems today. Most of them will not be this hard, but I figure if we do the hardest ones in class, then you'll be better prepared to do the ones on the exam, which will not be as difficult.